Hello and welcome to this session, in which today we're going to build a Christmas word search in C#. This session is part of the Festive Tech Calendar 2023, and there are many other great sessions, so I do encourage you to go and check out the website for more details. In this session, we're going to first look at the NuGet package I've put together in order to make building these puzzles easy. We'll also look at the sample code provided in the Github repo. Following this, we'll look at some of the logic that's implemented inside that package and what makes creating these puzzles slightly more complicated. But before we get started, let me introduce myself. My name is John Kilmister, and I've been a software engineer and architect now for over 20 years. As previously mentioned, this session is part of the Festive Tech Calendar, and this year they're raising money for the Raspberry Pi Foundation, so if you can, please do visit the Just Giving page and donate. In this first section, we're going to have a look at the NuGet package. It is the simplest and quickest way to build the puzzle in C#. We're going to start over in Visual Studio Code by creating a brand new .NET console application. From here, we will then pull in the NuGet package. Once the NuGet package has been imported, we can pull in the namespace. And start creating our puzzle definition. This is done using a Fluent interface. So we create a new Wordsearch builder, specifying the dimensions of the grid, so 10 letters by 10 letters, and then use the method with words to add in all of the words that we want in our puzzle. As this is a festive puzzle, we're going to go with festive words. Once we've added all of the things that we want to add, we can just call the build method. So we now have a fully built puzzle, but we need to display it. So I'm just posting in here some code that I've previously wrote that loops through each row and each column. And when we call .NET Run, you can see there is a fully populated puzzle. This shows the most basic usage of the package. There are many other methods and much more that we can do with it. We're now going to have a look at the second sample that is available on the GitHub repo. And this is a full web application and gives a much more appealing user experience. What we can see here is the sample application running. It allows us to specify the title, the difficulty, easy, medium or hard, and then the list of words. And the words are just comma separated. We click generate, and then we have the option either to view it as a web or as a PDF. When we view it as a PDF, you can then print that out. The solution is also provided with the words highlighted. You can have a look at all the code for this on the GitHub repo to really help understand how to use the NuGet package. In the second part of this session, we'll now have a look inside the NuGet package at how the puzzle is built. When structuring a grid in C#, there are two ways to do this. We can either use a jagged array, an array of arrays, or we can use a multi-dimensional array. Both are completely valid. However, the jagged array is more performant, and there's more details on that in this Stack Overflow post. The downside of using an array of arrays as opposed to a multi-dimensional array is the initialization. However, using the dimensions of the grid, we can loop through and create blank entries for each cell in the grid. Now we have our grid, it's time to start looking at how we place the words. Before we look at the code, let's take a recap on how our word search works. We can place words left to right, top to bottom, diagonally top left to bottom right, and diagonally from bottom left to top right. To make the word search more challenging, we can also reverse the words. I've been describing these directions in relational terms, left to right, but a much more concise and accurate way is that we can use compass points to describe the direction of the words, and that's how we're going to be using it in the code. So that gives us a summary of the different positions words can be in the grid. But in order to add a number of words to the grid, we need to do this in a bit more of an intelligent way to make sure the maximum number of words fit. If we just add the words in any random order, we could run the risk that the final word doesn't fit because there are not enough spaces left. If we're to order the words so that the most complex words and the longest words are fitted onto the grid first, it means the smaller and shorter words can fit in and around it. We do this in the code by scoring each word, allocating a point to each letter based on the frequency that letter is used in the English alphabet. The longer words will end up with a higher score because they have more letters. However, words with more vowels will also score highly. Now let's look at how we might place one of the words. The first thing we do is remove all of the characters that we don't want to show in the grid. Spaces, hyphens, numbers. Then we take one of the many word placers. These are the bits of code that will decide if a word goes left to right, top to bottom, or however. Once we've done that, we then take the word and try and place it in the grid. If that doesn't work, we will then try with a different word placer, i.e. a different direction. Finally, once we've found the word, we will place it into the grid and add it to the list of solutions. So I talked about the word placers, and these are the blocks of code that choose how we place a word in the grid. And there's one of these for each of the directions that are available. We're going to look at the horizontal placer that places words left to right, or how we refer to in the code as the east placer. All the placers work in pretty much the same way and actually share a lot of the code. So although we start with this placer, you can apply the logic to all of them. For the rest of this presentation, we're going to use a simple 6x6 grid. The first thing all the placers do, they take the length of the word and then look at all of the possible cells that word could be placed. In the code, we do this by creating a list of all of the x coordinates and all of the possible y coordinates. Here we've got the grid that is 6 wide and a word that is 4 long, and that limits down where we can actually place the word. I've placed a word in the grid already to make it slightly more challenging, and highlighted here all the places in the dark blue that the word tree could possibly start from. As you can see, it can't start more than 3 columns to the left on a horizontal placer because we run out of room. At this point, we don't look at the other letters in the grid. Now we have all the possible positions, the next step is to shuffle those, and we'll work through them one by one. We'll take a first random x and y coordinate and then try and place each letter in turn. First the T, then the R, then the E, seeing if the cell is empty or the same letter that we're trying to place. If it fails, as it has done here, we will then go to the next random location, which is here, and then once again try and place the words, starting with the T all the way through. Once it has been successfully placed, we then take that word and apply it to the grid before moving on to the next word, potentially with a new placer. If the word cannot be placed, there are no suitable locations, using this east word placer, We will then pick the next one from the shuffled list of places. If we have gone through all the places and all the possible locations and it still can't be placed, then the word is just excluded from the solutions list. So what does the code look like for each of these places? Well, actually all the places share 90% of the same code. When we want to actually get a cell location for the next letter in the word, we use this simple method here. This method takes two parameters, a starting cell and an offset, and the offset represents the index of the letter in the current word. Using this, we can calculate what the current cell will be. The key part of this is the direction to col delta and direction to row delta, and this multiplied by the offset will mean that the word starts travelling in a horizontal, vertical or diagonal direction. If we now look inside that method, we can see that the directions north, northeast and west will move the row back one. If we go south, southeast or southwest, we're moving the row one to the right. And if it's anything else, it doesn't change. This is the case for our east placer that's placing a word horizontally. In that case, the row delta is not going to change. When it comes to the reverse words, this is a simple decorator pattern that will just reverse the word before placing it. Now we've placed all the words in the grid, we need to fill all the remaining gaps with random letters. We could use an even distribution of random letters. However, that means the grid would have just as many Z's in as it does E's, which is not really what we want in order to make it a challenging puzzle. To solve this, we can pick a random letter weighted on its frequency of use in the English language. And luckily there is a Wikipedia article that gives us all the figures that we need. Using random letters can, however, lead to unintended consequences, generating additional words that we would not want in our puzzle. In this example, we've ended up with an undesirable word, although it could have been much worse. So how do we get over this problem? The first thing we need to do is gather together the list of explicit words we don't want to include. Now, luckily for us, this work has already been done. There's a nice GitHub repo that has text files in multiple languages listing out the most common profanities. Once we have this list, we can then solve our word search using each of these words to see if they're included, and if they are, then remove them. So how do we go about solving a word search in an efficient way using C#? Well, it turns out, after a bit of research, that the way humans solve a word search is exactly the same as how we need to solve it in code. There is no more efficient way. What we do is we start in the top left and we look for the first letter of our target word. We go through each cell until we find that target letter. Once we do, we then look around and we look for the second letter. If that's not there, we move on. If it is there, we follow the path down until eventually we have found the entire word. So just like we would as a human, it's done exactly the same in code. So, the process of removing the bad words are to loop over each of the bad words in our list, check that the number of letters in that word is not wider than the entire grid. If it's not, then we search through the grid using the solving algorithm we've just talked through. And if we find a match, we then need to replace each letter with another random letter, ensuring that we're not overwriting any of the letters that are actual parts of words in the grid. As mentioned before, all of the code for this can be found on GitHub. Now we've completed our puzzle, we've put our words in there, and we've populated it with safe letters. We probably want to be saving the puzzle for later use. We could simply serialize it to JSON. However, the NuGet package goes a step further, supporting the IPUZ format. The PUZ format is a commercial format used mainly for crossword puzzles. And someone came up with the idea of creating an open format called IPUZ that supports crosswords but also supports a range of other formats, including word searches. The NuGet package provides formatters to output the JSON in the IPUZ format. So if you are interested in this, do take a deeper look at the source code in GitHub. This is just the beginning, and there's much more that we can do with our puzzles. We could create shaped puzzles so they don't have to be square. We could add the ability for a snaking puzzle where the words are not in a straight line. And we can add additional support for multiple languages. So if any of those interest you, do feel free to reach out and we could consider adding them to the NuGet package. Thank you for taking the time listening to the presentation today. As mentioned before, all of the code is available on the GitHub site, along with a number of UI implementations and examples. If you are interested in just building the puzzles and not necessarily looking at the inner implementation that we've talked about today, you can just use the NuGet package, which is available now. Finally, I'd like to thank the organisers of the Festive Tech Calendar, and I do encourage you to go and check the other sessions that are available on their site.